introduce you the chair of the MuTaLig COST Action, and I also, on this occasion, acknowledge again the cost for the contribution to the school. And he's Professor Stefano Alcaro from the University of Magna Grecia Catanzaro, and he's going to have his presentation about the MTD approach and the Chemotheca tool in the MuTaLig COST Action. So, please.
So thank you very much for the introduction. I would like to start acknowledging the organization of this school, and in particular Professor Limongelli, for involving us in this important event. As already you know, I'm the chair of this COST Action that started actually in this place where you are now. So for me, it is a big pleasure to be here again, not for the annual meeting as it was last time, but for a school that is very well organized. And so thanks again for everything. My talk will be very general because I would like to stimulate you on some, in our opinion, important aspects that are related to the drug discovery using the multi-target approach. So in my presentation, I will spend a few words just explaining to some of you that maybe don't know well some concepts, how is the multi-targeting approach organized on. And then I will tell you some other things related also to the Chemotheca tool that is one of the issues that you can use. You can log in and use for your work. First of all, we start with the difference between the so-called the classical approach, the one drug, one target, that, by the way, was able to let us discover many important drugs. So this approach is still important. But for complex disease, like, for example, cancer or neurodegeneration, or also infectious disease, we know that the key targets involved are always more than one. And the idea of targeting them possibly in one compound is why now we move from, let's say, the classical to the one drug, multiple targets approach. This is, in theory, a simple approach, but it's not so easy to create compounds that are able to target what we want and to avoid eventually targets that are related to side effects. Even the side effects, as you know, is always present also in the classical approach. So just to explain some of the reasons of the multi-targeting idea, let's briefly try to compare three different approaches that we can use in therapy. You know that for cancer, for all the other complex disease, we often need to use a drug combination, the so-called the drug cocktail, okay? This is something that it is, you know, in practice very popular, and in some cases the only way to fight against this disease. In some cases, we have also the opportunity to combine in one pill two or more drugs. And this is the so-called the fixed dose combination that has some advantages, even is not the best solution. Why? The multi-target drug, maybe it is what we have in mind that we would like to use as the future optimized drug. If we combine actually the three approaches, we have two main issues that are problematic in the case of the combination of drugs. The drug-drug interaction and also the patient compliance that, by the way, are always difficult to fight with. In this, in the single-dose combination, we somehow reduce one of the two problems. even the drug-drug interaction is always there, because when we use this in combination with other things, it is possible to have this problem. While in our aim, the multi-target approach could solve at least those two problems. Now, the problem is how to do it. How is possible to combine the positive effects of, let's say, two drugs that here you see depicted in a blue and a yellow balls in one better compound, multi-target compound. Obviously, the obvious solution could be to link them and to create, obviously, compounds with a higher molecular weight. That, you know, it's one of the problems that we can have for drug-like properties. We can try to reduce and to fuse somehow the two compounds in one, let's say, smaller compound, and this is okay, another option. But in my mind, probably what is the most interesting thing is try to merge them. And when we think about merging this compound, we consider the pharmacophoric features that are related to the two compounds active in compounds that maybe are not chemically related with the parent active molecules. This means that we can explore new scenarios in terms of chemical space, and obviously also getting advantages, for example, for patenting compounds and so on. Where is the starting point? Obviously, we can start our job with existing compounds. And among many compounds that we use in therapy, there are active multi-target compounds that are able to exert the effects also against other targets. Aspirin is one example. But probably the most interesting example that we can bring in our literature, we can find from our literature, is the bad example of thalidomide that you know very well, is the drug that causes a lot of problems in pregnant women and in inborn child. Now, this compound is able to be considered for other important disease. And if a compound like thalidomide can have a second life, this means that probably we can use this approach for example, repurposing drugs. That is one of the issues strictly related to multi-targeting drug discovery. I want also to mention other example. Just another one, for example, is related to the acute myeloid leukemia, a cancer that has a lot of partners involved, and by definition, it is a complex disease. We have a set of, let's say, traditional chemotherapy agents that were used, but most of them are affected by drug resistance because they don't act probably against the multiple targets. So as soon as the cancer develops the mutation to some target, this compound is not effective anymore. So we had a lot of examples of other unrelated compounds in terms of chemistry to the parent first set of agents. And among them, I just want to point your attention on a couple that are those two active molecules, sorafenib and sunitinib, that are in our case, in our mind, probably the most successful example of multi-target drug. Because, for example, sorafenib can act against, as you see, 7 different targets. This is probably an exception, but it is very important to find compounds with this profile because we can use them in different scenarios, in different disease. By the way, in this case, we have also a very important information related to the knowledge of the binding of the sorafenib against, for example, the BRAF complex that you see here. also the P38 kinase complex. So here you have an idea of the deep mechanism of action, and you can compare the different binding modes in order to perform eventually better set of optimized compound, and again in the case of VEGF complex. So in other words, if we have the support of structural biology, we can really perform multi-targeting optimization. That, by the way, you know, is what we usually found in protein data bank and in other database that allows us to do it every day with new tools, with new targets. Now, the point is how it's possible to combine, for example, in one key, two features of the keys that we want to implement. It's a really big job, it's an important job, it's hard because when we introduce modification, we can have obviously side effects, but it's true that we have computational tools able to do that. We can perform, when we don't know very well the structure of the target, the pharmacophore-based design, but in many cases, we can do it because, as I mentioned in the case of sorafenib, we have deep information about that. So with this in mind, basically, we tried to implement in one project what is now the cost action MuTaLig. So basically, what we tried to do in our submission that started in 2015 was to create a network able to complete the preclinical development of multi-targeting drugs. We use this logo in which you see here inside many different things, including natural compounds, including repurposing, including polypharmacology, synthesis, and drug discovery by rational design. But in the aim to speed up the discovery process, we also created a tool that is called Chemotheca, in which we try briefly to speed up the information, the connection among the different groups. With this aim, we started our work, and I will briefly mention you the structure of the cost action just to know how we, designed it. There are 4 working groups. One is related to new chemical entities. That means people working in the lab, synthesizing or extracting molecules, okay? Another working group related to the biological and biophysical test. It is very important because we need a direct feedback of our prediction and our ideas. But 2 working groups are related to the computational part, because we need at that time to create the Chemotheca tool, and this is just devoted in working group 3 to the chemical database management and development, and the other one to the intensive simulations, mainly related to virtual screening and other tools. So with this idea, we started only in 5 partners. Here you have some information if you want to have a look at the website. The cost action is still active for a few months, but as you know, this is our last training school, and I will mention later the schedule that we have in mind. We started with 5 proposers. My university is the PI, and the other 4 were selected, let's say, by chance. It's not true, because we tried to design as much as we could the best combination. We selected 2 inclusiveness countries. Probably you know that in Europe we have 2 sets of nations, and the inclusiveness are those that are preferred for any kind of activity, in which, for example, Portugal and Slovenia, but other countries in the East and in other parts of Europe are preferred. We selected at that time also 2 companies, one from Austria and another one from UK. And we were lucky because at that time we didn't talk about Brexit. Now this could be a problem. But fortunately, as I will say you, we overcome it because with the 5 original co-proposers, when it was accepted, the project immediately exploded in a number that now is up to 33 different countries that are basically related to most of European countries. There is probably a problem in the slide. Sorry. We can go. Yeah. Okay, let's go straight to the. Later, okay. The other one, the second. This. Okay, this one. Yeah. Yeah, this is fine. This is fine. Okay. 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 So as I mentioned, we are now 33 countries. And it is nice now to also look at the number of participants, because there is a sort of contact database that take into account the number of people involved as members, as a substitute, as organizers, as trainers, as trainees, and so on. We are now close to this number, 750 people. Probably at the end of the COST Action, we will surpass the 800 people. So this is, in my opinion, very important because, especially for young investigators, the COST Action offers a lot of opportunities that I will briefly say you at the end of my presentation. Because here, you see, it's not only based on meeting on training school. There are, for example, short-term scientific missions that are, probably some of you have already used this tool. It is still active. Up to the end of the year, you can still submit your request, and I will briefly explain you how to do that. But also we have ITC Conference Grants. That is a new tool that was introduced a couple of years ago, actually after we started. And it is related to people, to young investigators working in the inclusiveness country only, that may want to present in a meeting their results. Meeting, not cost meeting, so another kind of meetings. And this is another tool that you can use. Here, basically, we are close to the end. And every year, we had the same schedule, the same approach. This is the flowchart of our COST Action. We started in Brussels with the kickoff meeting. Here we have the first annual meeting organized by Vittorio, by the way, and a working group meeting in Budapest. Then the first school in which we presented, launched somehow the Chemotheca that was developed and still maintained by Francesco Ortuso, that is my closest collaborator in Catanzaro. And here, another important event for us. We started to collaborate with different organizations, like in this school, that is a second school. In that case, it was the European Workshop in Drug Design, organized by Maurizio Botta, that unfortunately is not with us anymore, and I will actually remind him at the end of my presentation for some ideas that we have in plan. Other successful ideas to combine in meetings 2 or different approaches. For example, the annual meeting we organize in Porto between two cost actions. In that case, epigenetic and the multi-target cost action join together. And this is, again, an added value because we contaminated the collaboration. It was really useful for us. Here, a working group meeting in Tenerife, an annual meeting in Malta. So as you see, many things running. And this is also another school, the last school that we have done before this. And this was the only school that we repeated twice because we had a large number of requests. This was done in Hamburg in December and then duplicated in March, organized by Sheraz Gul, that is a scientist working at Fraunhofer Institute in Germany. And in this case, it was related to working group 2, so biophysical test. And some of you maybe already have been also there. And this is, in my opinion, very stimulating. Here, another mixing, let's say, mixed meeting in which in France, by the help and the organization of Luc Demange, that is the organizer of the Young Medicinal Chemistry meeting of the French Chemical Society, we joined also at the end with the cost action and with the working group. So in my experience, working together and joining, like also in this case, it's a great opportunity. And absolutely, I want to mention also our last event that was organized in my place in Catanzaro. And again, it was organized in collaboration with another organization. By the way, the Paul-Ehrlich Medicinal Chemistry Network, that I am also the coordinator at the moment, is of the cost action, because we selected from there the 5 participants that then applied. And, but cost, as I will mention briefly at the end of my presentation, is also able to be the father of something else, because the idea is to use the knowledge and the network that we create for other application and other initiatives. Here, actually, the last meeting we organized in Catanzaro. So basically, we have still one event expected that should close in March the cost action, but maybe we are thinking to apply for other cost action, so maybe we try to continue it. We just discussed it also yesterday with Vittorio about this opportunity. It's hard to put together all these people and just leave the network to be, disgregated. We need to do something else. Here, just a few things about the short-term mission. As I said to you before, it is a very good tool for young investigators. Here, for example, you see people running from a place to another one just in the first year. We had other that are not depicted in this slide, but I want just to mention that there is still another deadline. So it is important, if you want to apply, that your proposal should be strictly related to multi-targeting drug discovery, because otherwise it is discarded from the commission that assigned the grant. Few words about the Chemotheca platform. The Chemotheca platform is the tool that allows to share information among participants. It was developed, as I said, by Francesco Ortuso in my place. Here you see how it looks like the front end, and how it's possible to manage compounds using also graphical tools. Now, I don't want to be very technical in my presentation, so I simply say that we have developed few months ago a tutorial, 3 tutorials, by the way, that can be easily seen and are freely accessible at the Chemotheca website, as well as at the MuTaLig website. So I invite you to look at them and to register, to try to use to play. And if you have any kind of problem, we can support you, okay? Our goal is to reach a number of compounds included in Chemotheca that will be submitted to the virtual screening, periodical virtual screening application that we do with the Chemotheca against multiple targets typically related to complex disease. Here, the website where you can find and register, and if you have any problem also you can contact Francesco for technical reasons. By the way, there is also a paper related to the development of the Chemotheca that you can download. Is an open access paper, so you can eventually also look at them. Outcomes of the MuTaLig COST Action. Obviously, are the results that we have done, not only in terms of publications, but also when we created all meetings. Up to date, obviously, you can find 10 of them because we still have 2 in progress. This one, that is the annual school, the last training school, and the next year will be also the concluding working group meeting. And so if you want to have an idea, just look at these documents, as well as to all information related to the initiative to understand, for example, where to apply for an STSM mission place or for some other ideas related to this. We have also organized special issues, one in Frontiers in Chemistry that also hosted the MuTaLig Chemotheca paper, and now is still running because it's, I mean, the deadline is closed, but still we have some manuscript to be processed in this special issue on European Journal of Medicinal Chemistry that was really a great opportunity for us. And in this, the idea is to start dedicating to Maurizio Botta the editorial that will be probably released this year. Maurizio Botta was one of our MC members, and you know very well how important is the impact of his research in medicinal chemistry. But also, we would like to do another thing that I just start to propose to my members, that is a dissemination product that also will be dedicated to him. And this will be probably released the next year when we finish the COST Action, probably by a webinar that can involve all of you if you are interested in this. Very quickly few information about one of the effects of the COST Action. We applied for several projects, including, for example, in Italy, the PRIN that was accepted, and it is part of, let's say, the knowledge that we have developed during the COST Action, but also, for example, in my place, a spin-off company that started a few months ago that is also responsible of the organization of the meeting that we have done in Catanzaro, as well as all disseminations that we will complete, we plan to complete in the COST Action. Here, I don't know if I have time just to briefly explain what we can do. It is basically organized on, again, the idea to implement a multi-target approach for services for pharma, biotech, agri-food, nutraceutical companies, but also to organize events that are related to the creation of, let's say, a profile, an expert profile that does not exist at the moment in the field of multi-target and polypharmacology. So the first issue obviously is part of the drug discovery stage and process that we know very well, and can cover not only the preclinical, but in some cases also the ADME prediction part that is usually in the second part of the development, as well as the applications with natural compounds. Because the concept of multi-target can work very well in compounds from nature that, by the way, are in most cases multi-target by definition. In this field, in our opinion, there is not enough science and not enough scientific approaches to support nutraceuticals. And maybe with this spin-off, we can try to help companies that usually work in that field to be more, more effective and more performing. Here, the other part that I mentioned is related to dissemination and training that is part of our mission. The concept is always the same, to start from the beginning of my talk, the one drug, one target approach to the polypharmacology approach. Here some good moments that we had, but we are very young because it was founded in December of last year. So still we need to look for future developments. Now I want just to go straight to the conclusions. The cost action is a great tool. It has been for me a great experience, and it is nice that a lot of young investigators were involved. I have seen that many collaborations started during the cost action, that a lot of people start to talk about the multi-targeting approach that, by the way, is not a perfect approach. Is a philosophy, an idea. And this obviously need to be confirmed and to be investigated in details. The Chemotheca is a tool. Is a tool to exchange information that can work very well in the case of, let's say, academic field, and not very well if you want to share information, for example, of patented compounds or maybe not yet patented compounds. That's why we decide actually to organize a parallel, let's say, approach by the spin-off that can ensure much better information of private institutions. And still it is active, so if you have any kind of ideas or you want still to keep in touch, just let me know. So I think I conclude my talk, and again I thank the organizers and all of you for your kind attention.
So thank you, Professor Alcaro, for your presentation. So guys, have questions? No? Curiosity about the cost action? No?
So thank you, Stefano, for the very nice talk. Guys, I think it's an important opportunity for you, because I remember that when I was a PhD student, I didn't realize how many opportunities I had outside. These are opportunities to travel, to do visiting in some groups that you may be interesting for your project. So it's really a great organization, I would say. I enjoy the time with them. I also got many opportunities. I started some important collaboration that now are ongoing with a couple of groups, one in Germany and another one in Greece. Iliana is in the audience, actually. Yes, she benefited of the cost action fellowship. So what I will expect from you is curiosity, question, how to join. For instance, a question that I have for Stefano is about to speak about the next step, the next cost action. So some good ideas may come also for you, your feedback, wherever. Most of you are part of the cost because you are here, thanks also to the support of the cost. So any kind of curiosity, request, information, please don't be shy. He's the chair, so he knows more than everybody what you can, how you can participate in the future, how to do a cost action, for instance, how to write a proposal, what the things, what we would expect for the future. That's it. So please don't be shy and just raise your hand and start a very fair discussion. It's your chance, I would say. I didn't have it when I was a PhD student. That's the point.
I would like to comment that maybe ideas could come from you directly. I mean, if you start thinking with the, you maybe belong to different countries, to create your own proposal, because we now are able to interact directly with the cost association to look if ideas and proposals from you can be appropriate for the application. In my time, when I applied, I had no contacts. And actually, as I said to Vittorio yesterday, when I applied, the minimum of the countries involved was 5, and we were 5. And someone said to me, 5, you have no chance, because it's true that it's 5 the minimum, but if you want to be affected, you must be at least 10. So I said, okay, it will be a tentative, and that's it. And I didn't realize that was probably, we were right, and maybe also lucky for the composition. Now we have much more information about that, and we can have feedback. And the feedback is welcome, especially if the applications are from young investigators. So the key points are young investigators, gender balance, this is very important, inclusiveness countries, and obviously a very good idea. So
it's network, it's extremely important for us.
Do you have some project with antibody drug conjugate in the future?
This is, in my opinion, very important, especially if private institutions are included, because the point is how to, is the same also in the case of small molecules, but especially in antibodies. You need to also to include in your application someone that is able to scale up the process. So if I can suggest something, this could be appropriate, especially in antibody field.
Other? So let me do this question. Okay, let me do this question. Okay, first question you already answered. So private companies can be part of the cost action.
Sure.
Clear.
We had two out of 5.
I think also for people, because people,
at the beginning
there are some students, some people that work in the companies. Second, suppose I'm one of them, okay? I'm doing a project, and my project is Alzheimer or other things, whatever. Of course, I have to look into the cost side to see which kind of cost action is already active. Somehow
yes,
to join.
This is very important in order to avoid duplication or similar things that maybe can prevent the acceptance. Yeah.
So being part, this is a message I'm just discussed with you just to show how cost works, because I didn't know before I joined them. You can look for a cost action and can just join for free. And it's extremely important because it's networking. You can go to the meeting, no collaborators, so you can find good collaborators, or you can involve a collaborator in the cost action that you joined. And this provides funds to travel, to meet, to organize meetings. It's extremely important, guys, because there's no money outside. Yeah. We have to look for that.
And for, I also would like to add something. Usually there are 2 calls per year. One is in October, and the other is March, more or less. As soon as they are accepted, okay? Let's imagine that we have a cost action just accepted with 10 countries, okay? And among those 10 countries, there is not your country, okay? But you are interested in the cost station. You can immediately ask your contact point in your country to be included. This means that you basically became a member, okay? And if you are a member, you can get the benefits of all traveling and the contacts that is implemented. This is automatic because I mentioned we started with 5. After the acceptance, after 1 month, we arrive up to 25 and then to 33, okay? And all those that were added is because they looked into the cost action accepted, just accepted project and applied for being members. This is also very important.
Hi. Regarding the fundings, you're funding a person, a project, a team?
Okay, it's an important question. Cost Action cannot support research, only mobility and organization of meetings, training school, working group meetings. So if you apply, for example, for CTSM, it is a personal grant as well as from the ITC grant. So basically you are reimbursed or even partially, because you know most of you are granted, but it's not simple to cover all expenses. Is a sort of, in this case, a sort of little grant that helps you to be here. So it is personal, basically is based on this. The only exception is the organizational meeting that should arrive directly to a department that organizes it.
What I can say that, believe it or not, without the cost, this school couldn't happen. Because you can find, there's a CAM, important, they measure, contribute, the funder, then we got Novartis and others, but cost action was fundamental, otherwise it was not possible for you to come here. You stay here for 1 week, you know how expensive is Switzerland. So even though it's partial, it's important. It's the same for the short visit fellowship. So it's really important to look at. I have a question for you. It's about the next European framework program. Okay. What could happen with the cost action? Because I'm fully support of cost action, as you can understand. But my question is, this will be renewed or not as a program?
Okay, renew is not an automatic option. By the way, they never ask for renewal. They always ask for new applications. So one option could be, for example, to use our network for specific fields. For example, multi-targeting in neurodegenerative disease.
The activity will be renewed, so cost action will stay with the new program?
It's another application, totally.
No, I mean, your Horizon 2020 is going to finish.
Yes, also in Horizon Europe, it is.
Okay.
Yes, it's always there.
Good.
By the way, this is probably one of the oldest programs in the European community, because it started in 1971, if I remember well. So it is before the Erasmus.
So we can understand.
It is. But every new asset in the European community always supported. So
this once more highlight how communication is important. I didn't know this date. I just knew about cost action 5 years ago, 6 years ago. It's that's why.
And actually, they are working a lot for communication, and this is one of the issues, because maybe is not well known the presence of this project, of this program.
I have a question regarding the actually technology transfer.
Yeah.
How are you guys connected to the industry, and how do you bridge the gap?
Okay. In the case of our spin-off experiment, this is just a technology transfer from my university for a small company that is unrelated with other companies. So it is simply an academic spin-off. Okay. Well, we can join other companies in order to extend and to include eventually in the spin-off the presence of industries, because this is part of the mission that we have. And this is possible because it's a private institution, basically. Yes, there are many other cases in which they included also big companies inside. Yeah.
Just a small question. Except of PhD students, does cost support also master students?
I think so. Yes, because the preferred profile for the cost action is young investigators with PhD degree, no more than 8 years old, let's say. So this can also include master's students, sure.
Okay, so thank you very much for this interaction.
Yes,
of course.
I'm here for the whole day, so
you can ask him whatever you want.
Yeah,
about the costs.
Pleasure. Okay.
Thank you again. And now we have to move on with the program. So
Daniel, for the invitation, giving me the opportunity to come here all the way to Lugano. It's quite a trip. So my background is in bioinformatics. So in my talk, I will guide you through 4 recent research projects that my team has just finished. So I hope this can give you some idea of how we can actually leverage the power of machine learning technologies in order to solve some of the typical biomedical classification problems. So at Monash University, our research is primarily focused on developing, deploying machine learning, data-driven machine learning techniques, address a number of open questions in 4 research areas, like structural biology, genomics, microbiology, and cancer biology. So in order to solve these questions, we resort to and develop and design a number of different bioinformatics tools, algorithms, pipelines, software, and web servers. And also in this process, biological users or experimental scientists, they could further borrow the power of the design bioinformatics to facilitate their experimental discovery and facilitate like experimental hypothesis generation process. What is machine learning? Is a subfield of computer science that gives the computer the enormous from generate the knowledge, build up the model, and to produce novel testable prediction outcome that can be ideally validated back in the lab. Machine learning sitting in the core of the fastly developing artificial intelligence. In machine learning, the data is fed into the model, and in this process, a number of decisive rules can be defined. And the computer could further utilize the rules to make the new prediction. Therefore, machine learning technology can be utilized by the computer to automatically learn. So it can automatically turn the data into the predictive pattern and the predicting output. So that can enable data-driven predictions. So it can better inform the design or inform the guiding of novel experimental design. So in this process, the power is reflected by the novel biomedical knowledge generated by the model. Mathematics, there are a number of questions that can be better addressed nowadays by using data-driven machine learning technologies. So this just give a list of some exemplar research projects or questions that can be addressed using machine learning technology now. So this includes, for example, predicting the secondary, tertiary, and quaternary structure, predicting the flexibility and disorder in protein structure, and also predicting enzyme-specific cleavage target as well as specific cleavage size. Also, like predicting bacteria-secreted effector proteins, either from the sequence data or from structure data as well. And also like cancer diagnosis or classification or subtyping from the image data. Image data here means the histopathological image data. And also predicting what proteins can better crystallize and hence be structurally solved, generating its 3D structure. I also like predicting drug targets, predicting functional impact of SAPs like single amino acid polymorphisms. Also predicting like other functional variants given the sequence genome data. Also like in the end, I also talk about in another project, it's called developmental meta learner that can enable the automated machine learning model construction from heterogeneous data types like sequence data or other different types of data. So this is the first project. It's predicting protease-specific substrate cleavage size. So I have been working on this topic for a long time, I think more than 10 years to date now, since I commenced my position at Monash University 11 years ago. So my student and I published quite a few papers to address the protease-specific prediction problem. And in this talk, I mainly focus on one most recent work published in Bioinformatics. Just a little bit about protease biology. So protease actually considered as playing a central role in the life and death process. This is because across all the organisms, protease like playing a fundamental biological activity from our daily life to even like getting rid of unwanted proteins or misfolded proteins. The cell needs to use the function of protease in order to either degrading the targets into smaller pieces of peptides or help the human cell to better digest food. So in many of those cases, like diseased states, the protease malfunction of protease lies like in the underlying role, causing like some disease states. For example, there are some mutations that occur at protease active site. In these cases, the activity of the protein normally like either upregulated or downregulated. So that may lead to like disease association. And in many of the cancer metastasis process, there are some particular protease families implicated in such process, like matrix metalloprotease. So according to the catalytic mechanism of protease family can be classified as like serine protease, cysteine protease, and threonine protease. This is called covalent catalytic protease. And the other type is non-covalent catalytic protease, like aspartate protease. And according to the mode of substrate cleavage by the protease, its protease can be further classified as like endoprotease or endopeptides or extrapeptides or extraprotease. So whether a protease is considered as endopeptides or extrapeptides, it depends on the manner the substrate target is cleaved by the active site pockets of the protease. For example, in the case of endoprotease, the substrate could be fully accommodated by the active site of the protease, hence be cleaved from the between. In the ether peptidases, the subject could only approach the active site of the protease from one side. It cannot be fully accommodated. So to better define the substrate cleavage or biological specificity of the protease types, so in the literature, there is a nomenclature, classical nomenclature. So in this classical nomenclature, the subject cleavage site is between the P1 site and P1 prime site on the substrate side. But on the corresponding protease side, the residues are named as S1, S2, S3, S4, S5 in the upstream from the cleavage site. Downstream, it's called S1 prime, S2 prime, S3 prime, S4 prime. This nomenclature is crucial because it gives us the idea or the knowledge of the difference of the substrate specificity of different proteases. And also, in order to develop a data-driven sequence-based bioinformatics model, we need to extract the local features or information that better delineates the specificity of the protease. There have been a number of studies done in the literature that focus on designing a much better computational tool for classifying, identifying the potential targets or cleavage sites given the protease, their subsets of protease, their substrate sequences. There have been still some challenges though. For example, for many of the proteases, like aspartic proteins, particularly like cell apoptotic caspases, those caspases, they are well known to have like a cleavage site, subject cleavage site sequence motif, like DXSD motif. So normally it's relatively accurate for us to build a motif-based model to predict the potential substrates and targets for the caspase families. However, for other proteins like thrombin, like matrix material protein, it's much more difficult. I will show later. So for bioinformatics model assessment, normally we utilize a number of different measures. First, the subject dataset of the proteins in this study is extracted from the Murrow database. It's curated by a group from the European Bioinformatics Institute. It's the most important public resource providing annotations regarding protease, substrates, and inhibitors. So in this study, in order to generate a sequence-based machine learning model, we need to label the data. So in label the data, I mean, we need to have both the positive, like well-known, experimentally validated cleavage sites, and also negative data, like non-cleavage sites. So these annotations are coming from the Murrow database. And then we utilize a sliding window approach to extract the local feature surrounding cleavage sites of interest. Whether it's a cleavage or not will be recognized by the model. So in order to evaluate the performance of our development tool, DeepCleave, we used these primary measures like sensitivity, specificity, accuracy, and Matthews correlation coefficient, F-score. So in bioinformatics, these are commonly used measures for evaluating the predictive performance of the model. This is a flow chart of our developed DeepCleave methodology. So there are several features of this DeepCleave method compared with existing literature paper. So it is, to our knowledge, this is the first deep learning-based algorithm for predicting cleavage targets of proteases. Second, it utilized a very simple sequence encoding approach in order to capture the local determining information of the subject specificity. We call it one-hot encoding. It's very simple. In machine learning, it's straightforward to use, very easy to be encoded and feed into the model. The overall flow chart of DeepCleave is like that. We start with the data set curation from Murrow's database. We curate the data set by classifying the substrates of different proteases. Specifically, we focus on two protease families like caspase family and the matrix bacterial MMP family. There are a number of types affiliated with each of the protein family. And we try to develop a deep transfer learning-based algorithm that first try to mimic the subject specificity at the family level of the proteins. Then we try to build a model, refine the model to predict the potential subject cleavage size for individual protein types, like MMP1, MMP2, MMP3. And then we separate the dataset into both the validation, like the benchmark training dataset, and also the independent test dataset. And we train the model. The detailed network architecture of DeepCleave is reflected in this panel. We start with a very simple encoding scheme, one hot encoding, then using a number of different convolutional layers. And in this process, the deep learning algorithm can learn better representations of separating the positive sample and negative sample. The final output of the deep learning neural network represents the probability score of a given site or residue being predicted at either a cleavage site by the corresponding protease or non-cleavage site. So this is like the overall flowchart and structure of the methodology. In this figure, we show the performance difference between the two protease family, caspase family, and MMP family. There is difference, like I mentioned, relatively easier and more accurate to predict cleavage targets because majority of the cleavage site contain the canonical DFSD motif, very easy to recognize. Reflected, because for training deep learning model, it only takes about 400 epochs for the deep learning model to converge and attain a relatively higher and stable predictive. But in the case of MMP family, it's much more difficult in terms that it takes more than 1,000 epochs for the model to converge, reflected by the fact that the accuracy attained by the deep learning model for predicting caspase cleavage sites, the accuracy is close to, it's more than 96 or 7. But in the MMP case, the accuracy is about 80%. This is the performance comparison between the protease-specific cleavage prediction. We compared multiple different variant models of deep learning. For example, with the attention mechanism, without the attention, without the final second fully connected layer as well. And we show that the final optimized model of DeepCleave attained much better accuracy compared with different variant models. And in this model optimization process, we can show that the very simple one-hot encoding-based model through the deep neural network process, it can gradually learn better feature representation and improve the prediction performance in terms of these AUC scores. This is like the classification capacity comparison between different types of models or feature representation. As for the one-hot encoding, just based on very simple one-hot encoding without building the deep neural network model, we can see that several different types of cleavage site could not be well separated. However, if we compare the model performance, we can see that this discrimination capacity is better improved gradually from this process. And the final model generates much better classification performance. This is the receiver operating characteristic curves between the trained DeepCleave model and other existing state-of-the-art methods. For caspase 1, caspase 3, caspase 6, and also another 3 types of MMP family, like MMP2, MMP9, and MMP7, we can see that the performance of DeepCleave basically consistently achieve the best AUC values. And as an implementation of this project, we also provided an online web server. So users, biological users, who have the interest in protease biology and who want to identify their potential experimental targets, they could refer to the website and input the sequence of protein of their interest in the fast format and select any of the corresponding proteins to make the prediction. Or in cases where users have multiple sequences to make the prediction, they can upload a file in the fast format. The conclusions for the project example 1 is that we developed a new bioinformatics approach called DeepCleave, which is the first deep learning-based approach for accurate prediction of protease-specific subject cleavage sites. A DeepCleave utilizes a subject sequences as sole input, as the only input to make the prediction. This has some value. For example, in many of the cases, we don't know the knowledge of the structure. We only know the knowledge of the protein sequence. If we want to know which proteins could cleave this given subject and at what cleavage site positions, so they can easily input in the sequence as a sole input to make the prediction. And we also perform benchmarking experiments by comparing the performance of DeepCleave against several other predictors. And we show that DeepCleave, trained on deep neural network model, provides competitive performance. This framework can be easily extended to address other typical sequence-based classification problems, such as predicting protein active sites, predicting protein-protein interacting sites, and also predicting some post-transcription modification sites as well, PTM sites. So the framework is very easy to be extended. This is the first project. The second project is like identifying the effector proteins of bacteria type 3, 4, and 6 secretion system. We have been working on this project for a number of years, I think more than. Just a little bit background about bacteria secretion system. So there are so many different types of bacterial pathogens. One common mechanism that bacterial pathogen that can invade the human host is through the secretion effector system. In this process, the bacterial pathogen can secrete their effector molecules. The molecules can have interaction with the other proteins or interacting partner from the host cells, and hence, potentially, they could hijack the human or the host pathways in order to manipulate the host immune pathway or evade immune detection in order to achieve and enhance the pathogenicity effects. So in many of these gram-negative bacterial pathogens, over the evolution process, they have evolved multiple different types of secretory effector secretion system, like type 3, type 4, type 3, type 2. This is like just like a cartoon representation of the structure of different types of secretion system. It's like the gun, right? So in some cases it's hand gun, some cases very like machine gun or very long with a very long tail as well. So we are very interested in developing a computational approach to recognize what protein effector can be secreted by the corresponding secretion system. And if so, are there any difference? Are there any characteristics or features that can be recognized, identified by machine learning? So we focus on the type 4 secretion system. The type 4 secretion system is evolutionary related to the bacterial conjugation system. In the early stage of the development of this bacterial secretion, its original role is to play a role as like supplying the nutrient, like to obtain the nutrient from the external environment. But through the evolution, now the bacterial type 4 secretion T4 system could secrete a number of pathogenic effectors, not just satisfying the role of obtaining a nutrient, but also like hijacking the immune system host cell as well. So in a recent study published in Nature Genetics, the author focused on identifying effector protein from one specific gram-negative bacteria, Legionella pneumophila. Legionella species, in this study, they found that there exist nearly 6,000 different effector proteins. And there are many more novel effector proteins waiting to be discovered. So some computational studies in this process. And we performed a recent survey indicating that the performance of this machine learning-based method needs to be further improved. Therefore, that motivated us to develop our new system called BImBS, Bacterial Secretion Effector Classifier for Type 4 secretion system. This is the structure of the BImBS. So we start with the Acute. First, we constructed a secretly effector database by referring to a number of public databases and also a recent literature. And the dataset into the training sample and negative samples. And we extract a variety of different feature encodings. And for each of the feature encodings, we train a corresponding classifier. And then we merge the prediction output of multiple individual single classifier together by using ensemble voting strategy in order to achieve a much better, accurate, and robust performance. And through this voting strategy, we show that effector protein non-effector can be better classified. So this is the structure of BImBS. Again, some of the prediction indicating the performance of different machine learning algorithms for predicting the effector protein. So the ROC code, like here, we use 10 different sequencing encoding. And for the 10 different sequencing encoding, we trained 10 different machine learning-based classifiers. And we made a comparison. We show that two specific machine learning algorithms perform the best, like support vector machine, shorthand at SVM, and random forest. These two machine learning perform the best. And then we proceeded with the construction of ensemble learning-based classifier. And we show that out of these 10 different classifiers, we can further generate an ensemble voting strategy by combining the prediction outputs of generated by multiple classifiers. And this specific encoding scheme performed the best. Implement to input the sequence data and then select either of the 10 encoding. Users are also allowed to press Alt button to select the most comprehensive ones to make the final analysis. It will be returned after submitting the task. The users can click the corresponding unique job ID or the job name and to retrieve the prediction result. Once the status is labeled as completed, user can click the corresponding button to retrieve the results. So for this project, new bioinformatics tool called BImBS, focusing on identifying effector proteins of bacterial secretion effector type 6 and type 6. And we are also trying to develop integrated informatics package that focus on integrating all the different types of secretion effectors. And the voting strategy and ensemble model, we show that lead to the best predictive outcome. So again, this machine learning framework can be generally applied to solve other protein, DNA, RNA sequence characterization problem based on the sequence data. This is the third example project. This one is very different from the former two project. So in the end of last year, there is a very enlightening leading work published in Nature Medicine, really open up the horizon for histopathological data analysis, automated histopathological data analysis. And in that work, the authors, the group from New York University School of Medicine, deep learning technology can be applied to perform automated classification or diagnosis from the histopathological image data. And the performance of cancer diagnosis is comparable to the human pathologist, but with a much better computational high throughput and also much better efficiency. That work really motivated us. So this is open source, fully automated pipeline. For many users without the expert knowledge in deep learning, it's very difficult to develop their own algorithms. So we are very interested in making available and automated pipeline that can fully automate the whole histopathological data analysis across all the major human tumor types. So we named this software called HEAL, hemotoxin and using image analysis pipeline. There are a number of functionalities that HEAL package could provide. For example, it can enable the user to perform cancer diagnosis, cancer typing, and subtyping, and also perform molecular gene mutation prediction from the image data, and also to provide the prognosis modeling as well. The input to the HEAL package only require two different inputs. One is the image whole slide, high resolution histopathological whole slide image, and also plus with the label. The label means, okay, whether this slide contains cancerous tissue or not. So only two very simple labels. Then the HEAL package could enable the user without less knowledge in machine learning to train the deep learning-based model and perform a series of automated function analysis like the data distribution, ROC curve analysis, and also the training loss accuracy curve of deep learning, and also the confusion matrix, and also perform the in silico labeling prediction of the cancerous tiles from the high-resolution image data, and also to generate some data visualization results to better facilitate perhaps users, computational biologists, or histopathologists to interpret the prediction generated by the deep learning model. The number of procedures that can be wrong, need to be wrong, like a slide tiling, dataset split, model training, performance evaluation, independent test, and the case study, and also the further follow-up analysis. So this analysis could be done by the HEAL package. I will not talk about this. This is just a distribution of the datasets supplied by users as a case study. This is the performance, ROC curve performance for cancer diagnosis analysis, like for classifying whether the slide is a tissue, normal tissue, or is any of the subtypes of the lung cancer, either Luke or Lude. This is the performance of the HEAL trained model at the patient level, this is at the tile level. The tile level means that in order to train the deep learning model, you have to, you cannot input the whole image into the deep learning. You have to use a sliding window to cut into pieces in order to generate a large amount of sample that can be learned by the deep learning model. So that's the tiling. And so the performance can be assessed by both levels, tile level and the patient level. And for the patient level, we need to summarize the prediction outcome at the tile level in order to make the final diagnosis, whether this patient contains cancerous tissue or not from the image. So the performance would be much higher at the patient level than the tile level. And another case study is that the HEAL package also enable users to make the prediction whether this image contains the gene mutation or not. This is like distribution of the most populated 10 genes from the TCGA. TCGA is one of the largest publicly available multiple omics together with histopathological datasets curated by the National Cancer Institute of the United States. And we show that for the 10 genes, at least 9 genes could be predicted with a reasonable AUC value from the image data without sequencing the gene sequence. And for example, some genes, like the KRAS, and also STK11. Both are kinase-related genes, and they could be predicted with a relatively much higher accuracy. This indicates that the gene mutation could indeed, at least certain gene mutation could be indeed predicted from the image data, from the patient's clinical image data. The final project example is iLearn. iLearn is our most recently developed bioinformatics package. It's considered as an end-to-end meta-learner for automated machine learning model construction from heterogeneous sequence data. Here, the sequence data, I mean DNA sequence, RNA sequence, or protein sequence, or peptide sequence. So at least 3 different types of sequences. It contains a full range of functionality, ranging from all the way from feature extraction, clustering, selection, normalization, dimensionality reduction, model construction for classification, and as well as better model selection, ensemble learning to the result visualization. So iLearn contains a lot of functions, including the feature extraction and also machine learning selection. It's meant to be developed to facilitate or expedite the research exercise of users who do not have a solid knowledge and background in machine learning, but might have the need to investigate and to make a use of their own experimental sequence data and to make the machine learning model. The architecture of iLearn is like that. This curation, users at least need to curate their own dataset from their own studies, separating into the training data and independent test. And then users can run the iLearn package to extract a variety of DNA features if their dataset is DNA sequence dataset, or RNA sequence features, or protein peptide sequence features, and perform the feature engineering analysis. And then they could use 5 different alternative machine learning algorithms to train the model. So all these functions have been made available and fully automated. This is just the feature extraction process. A few of the results figures that can be generated by iLearn is like hierarchical clustering, either in the 2D or the 3D scattering diagram, and also the ROC curve, the precision recall curve. These 2 curves are commonly used for evaluating the quantitative performance of machine learning models. So in many of these cases, users need to generate these curves and make a comparison of their different classifiers and optimize the classifier performance. And iLearn is available through 2 different sources. One is through the access to the Monash University, this URL address. Another one is user can download from the GitHub. There is a link given at the website that user can download a standalone software package, which is Python-based and full open resource. And for the DNA sequence and RNA sequence, user can conveniently click any of these buttons. And then they will be given the window to analyze their own sequence data. And at Monash University, our team have developed a number of bioinformatics tools in the last 3 years specifically. These tools have generated some high impact across the globe. This includes like 100,000 access from worldwide users, and also like leading to accumulation of more than 600 citations in the last 3 years, and users coming from 120 different countries. I list the majority of the tools that our team has developed in the last 3 years. It includes iLearn, iFeature. iLearn, I just described. iFeature is a feature engineering extraction analysis tool. DeepCleave, I presented as an example project 1. And there are some other ones like focusing on protein translational, post-translational modification, and functional site analysis, and also bacterial sequestration. There are a few other bioinformatics knowledge databases like Security PDB is a database, and also some other feature engineering analysis tools, and also RNA modification, DNA modification, and also some other ones. This is another database which we focus on creating a database like related protein functional PTM and with disease-associated polymorphisms. Just a little bit of insight I would share through over the so many years of machine learning practice. So machine learning has been considered as a black box. There have been a tremendous effort focused on recent years that focus on enhancing the transparency, explanation of machine learning, and to convert it from black box to the white box. However, in this process, the user, the domain, expert knowledge, I think, is still crucial. So how to better combine the user's own knowledge, biomedical knowledge, and leverage the power of machine learning. And in this combination process, that can lead to the best outcome, best possible outcome. Also, there has been still a lot of open challenging questions like how to better represent your samples, how to extract the most appropriate or informative feature that can enable a much better machine learning model construction. So a lot of these questions still open. And also depends on a lot of other factors as well. Depends on the context of your sample, depends on the size, or the complexity, or the layers of information that can be used to encode your sample. So there are lots of combination process. Yeah, finally, I would like to thank my collaborators, specifically Professor Jeffrey Webb. He's the director of Monash Center for Data Science, and Professor Raj Daly, who is my long-term collaborator. He's a cancer biologist, and also Professor Ian Smith and Professor Trevor Lisco, and my PhD students Fu Yi, Yanan, Jin Xiang, and Jericho, and also my collaborator, Dr. Chen Zhen from Qingdao University in China, and my collaborator, Professor Akusu from Kyoto University Bioinformatics Center. Thank you very much.
So thank you, Jiangning, for your kind presentation. So there is, some minutes for questions. Any question, guys?
Hi. First of all, please let me know if my understanding is not that much clear. So if I understood clearly that in your second project, you mentioned that there are a lot of gram-negative virulent bacteria for which they synthesize some kind of effector protein that help them to invade the host cell membrane. So, again, there are a lot of bacteria for which nothing is known about this kind of effector protein. So this is the database which collects all the information about this kind of known effector proteins of the virulent gram-negative bacteria, and on basis of all the available information, it generates an ensemble model, and from which we can get some kind of idea about this kind of effector protein for the unknown virulent bacteria. So is it correct?
First, about the availability of public available database. There are few databases available, but focusing only on specific type of effector protein like type 4, type 3, type 6. There are no comprehensive database available to date now. We are trying to curate one. We curate a secret EPDB, but focus on 3 types, type 4, type 3, type 4, type 6. But still, because this field is progressing very fast, there are a number of new effector proteins keeping discovered in the literature. So there is a very strong need to curate a more comprehensive and up-to-date one. Regarding the ensemble learning approach, we implemented the web server, but the source code are not available. If you are interested, we could share with you if you are interested in designing your own algorithm. Yes.
Okay, so that ensemble model is not available, but I mean, it is under process.
Yes. So, yeah.
Okay, so I mean, could you please elaborate on that? I mean, what is the algorithm behind this kind of machine learning? Like, on which parameters normally it focuses on in generating this kind of ensemble model?
There are so many different learning algorithms. So for our Bastion series of work, we use random forest SVM. We published a few papers. So in the most recent paper, we use deep learning as well. We also use like heterogeneous machine learning modeling. We coupled with multiple different machine learning, and we just developed a multiple layer of machine learning. Because those work I show is pretty much only single level, single layer, single level. You could develop a second level, a third level, and you could like through the feature representation learning, you could condense the most representative features and generate the most robust machine learning model. So you could use multiple different ones. Yeah. It depends on again on your question and on your own data set, and you know, yeah.
Oh, thank you.
Other questions? Daniela? Just wait.
Yeah.
Your deep learning approach is sequence-based approach, right?
Yes.
In predicting the cleavage sites.
Yes.
My question is about the structure of the proteins. I mean, in your deep learning approach, you can also add information coming from the structures of the protein, because I mean, sometimes some sites can be accessible to the enzyme after conformational changes, or
Yeah.
so my question is, if you can include also structural information, you can improve the prediction of the cleavage sites.
Yes, that's a very good question. So there are two ways of incorporating the structural information. So one way is actually to make the prediction from the raw sequences. You can predict the sequence information. You can extract or predict sequence-derived structure information using other third-party software like secondary structure prediction, disorder prediction, solvent accessibility prediction, active sites, or this. Yeah, that's predicted. So you could also perform structure-based modeling to extract the structure neighborhood information. We didn't develop deep learning approach that incorporating all the information, but we developed a non-deep learning one. It's called random conditional random field, with incorporating both the sequence real 3D structure plus network features. Yes, that work is accepted by this year. Yes, yeah.
Okay, thank you.
Any more question? No? If that is not the case, we thank again the speaker.
Thank you very much.
Professor Song. So now we have the coffee break. Since we are a bit late, we have 22 minutes, so please come back at 11:50.